Around IT in 256 seconds by Tomasz Nurkiewicz. Episode 52. How computers work.
Today I'd like to explain how computers work, from the ground up. It all starts with an electric field. It's a place where charged particles like electrons are attracted or repelled. The electricity flows through a piece of wire because of the difference in electric field potential on wire's ends. This difference is known as voltage. Then comes diode. It's like a one-direction valve passing current only one way. You can build a diode using vacuum tubes. A tube is a fairly big glass device that needs a lot of energy and often breaks. But you can also build switches and amplifiers using vacuum tubes. It's just one step from constructing large, clumsy computers like ENIAC. The invention of transistors changed everything. Transistors are much smaller than vacuum tubes. You'd need a very sophisticated microscope to see them. Turns out you can connect two transistors to create a very simple device with two inputs and one output. The output has high electric potential if and only if both inputs have high potential. Change high potential to binary 1 and you end up with logic AND gate. With a few AND gates you can build a 1-bit adder, a tiny device that takes 2 bits and adds them. Bits are numbers 0 or 1. If you connect 32 such adders sequentially, you can now add two 32-bit numbers. This is big. We have an electronic circuit that adds binary encoded numbers ranging up to 4 billion. But it gets better. Inverting bits of the second number makes it negative. So our device can also subtract. By adding one extra input bit, we control if we want to add or subtract inputs. Or maybe we want to compare which number is bigger, or apply logical AND of corresponding bits. We now have a device that takes two large numbers and an encoded operation. Depending on which operation we choose, the output is different. This device is typically called ALU, Arithmetic Logic Unit. ALU itself is too simple. What if we want to add 1,000 numbers, not just 2? We can build an extra wiring that takes the output of addition and feeds it back as input of the next step. That's how we can program ALU to perform multiple, very simple steps. We just build a CPU, reading a sequence of instructions from memory, feeding them into ALU and providing outputs. Outputs are stored into memory or fed back into ALU. Programming computers using machine code is tedious. That's why high-level languages like C++ or Go were invented. The compiler translates for loops, if statements, and so on into machine code. All this happens within an operating system. Yet another program that abstracts away the hardware. So the next time you open, for example, Slack, remember this. It's a JavaScript application deployed on top of Electron, written in C++, which was compiled to machine code that is loaded from memory into CPU. CPU decodes, caches, and invokes instructions. Data and instructions are encoded as binary, which in turn is converted into electric signals. The electrons flow through transistors, which produce output current. That's it. Thanks for listening. Bye.